Welcome to the Unit 3, Section 7 video on real-world applications of quadratics. So before we get to some of the real-world applications, of which we'll only do a few examples, let's talk about some of the methods that we have learned in this unit for solving quadratic equations. So we learned quite a few of them, and each of the methods come with their own set of advantages and disadvantages. So let's talk about graphing. That was the first method we learned back in section 1. Well, graphing always works to give you approximate solutions. You can always put it into your graphing calculator and figure out what those approximate solutions are, and you can quickly see what the number of solutions are by graphing. But the big problem is you can't always get an exact solution, especially when you're doing it by hand. You can't get any better than, say, an integer solution, because if the line goes between two integers, you know that's in between those two integers, but you don't know any exact value. You don't know if it's a half, a third, square root of 2 over 2. You don't know any of that. Also, you can't find imaginary solutions if you're graphing, because the parabola is going to either sit entirely above or below the x-axis. So you have no way of determining imaginary solutions. So graphing has quite a few limitations with it. With factoring, it's a good method to try first when you're trying to do it algebraically. It's very straightforward if you can factor it, but it's not so good if you can't factor, because one, if you can't factor it, then you can't use factoring at all. But the second is, if you have numbers that are large, it's going to be challenging to factor that quadratic equation if you have big numbers. So say you're trying to find two numbers that multiply to give you 465 and add to give you 32. That's going to be a bit more of a challenge. So you would probably not want to go that route and try to use something else that's going to get you to the answer quicker. Because remember, this is all about trying to find the best method to make it the easiest on us. That's why you learn all of these methods. These are all just tools that you have in your toolbox now, and you can pull out the right tool for the right equation. Using square roots is good, but when we did that, remember there are only a couple of specific cases where we could use square roots, and that was one, if you had an x squared term but no x term. So if you didn't have the linear term but you had the quadratic term, then you can easily use square roots. Or if it's in vertex form, you can do it that way as well. But then if you don't have a perfect square if you don't have a something that's already set up that way, you have to look to see if you have a perfect square trinomial. In that case, you have to factor first and then complete the square if it's not a perfect square trinomial. So completing the square is good, but sometimes that also can involve difficult calculations because you're working with big numbers. So that brings us to the quadratic formula. I always kind of view it as a option of last resort. It always works. It can always find exact solutions. It can always find you imaginary solutions. So why don't we use it every single time? Because some of the other methods may be easier. If you look at it and see that it can be factored right off, that's going to be much less time consuming and much less work than plugging everything into the quadratic formula to solve it for you. So you got to be thinking about what's the best method to use as you do some of these problems as you approach them. Because if they don't ask you to use a specific method, then it's up to you to figure out which method is going to work the best. And we will deal with that a little bit here in some of these application problems. So let's get into solving some real-world quadratic problems, because we've done quite a few problems learning all the methods, but we haven't really connected it to the real world yet. So let's see what that would look like. So let's take this first problem. A ball is thrown upward. Its height in feet is given by the function h of t equals negative 16t squared plus 64t plus 34, where t is the length of time in seconds the ball's been in the air. So it's being modeled by a quadratic equation. And that makes a lot of sense, right? Because let's draw what that looks like. If we have a surface, okay, Let's say that this is my ground. Okay? And we were to throw a ball into the air. It would take a path something like this, right? Well, what does this look like to you? It looks a lot like a parabola, right? So if the ball's going up in the air, we want to find out when does the ball reach a height of 96 feet. Well, it's going to hit 96 feet twice, right? Once on the way up and once on the way down, unless it happens to be the highest point. Okay? If it's the highest point, then it'll only hit 96 feet once. But let's assume that it's going to happen twice, that's not that ideal situation where 96 feet is as high as it goes. We'll find that out in this. Okay? So, first thing we want to do is we want to set up our equation. Well, we know it's being modeled by this. We know we want to find out the height is 96 feet. So we're trying to solve for t because we want to find out when. 96 feet is our height, so that's going to go in for h of t. So you're going to have negative 16 t squared plus 64t plus 34 equals 96. And now we're just going to solve this equation for t. So we're going to subtract 96 from each side. And that's going to give us minus 62 on the left-hand side equals 0. Now let's think about the method we want to use to solve this. I don't think graphing is going to be very practical here. What about factoring? Well, we've got some big numbers here. We've got to multiply negative 16 and negative 62 and get two numbers that multiply to give us that result and add to give us 64. I don't much want to factor that. So let's think about completing the square, or let's think about factoring, or taking the square root. If we took the square root of both sides, that's something we can't really do here because we've got a linear term. So that's out. Completing the square, same issue with factoring. We would have to deal with some pretty big numbers here. So let's move on to the quadratic formula and solve this using the quadratic formula. So we have t equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. It's not a bad idea just to write the formula down first. So our opposite of b is 64. We've got plus or minus b squared, so b again is 64, so it's going to be 64 squared, minus 4 times a, which is negative 16, times c, which is negative 62, all over 2a, all over 2a, a being negative 16 again. So let's simplify a little bit. We're going to have negative 64 plus or minus. If you do all that math under a square root, you end up with a square root of 128 over negative 32. Now in these real-world application problems, it's actually not a bad idea to get a decimal answer. Put this into your calculator and see what you end up getting, because negative 64 plus or minus the square root of 128 all over negative 32 doesn't really tell me what the time is. I have no idea off the top of my head. Is that 1 second, 2 seconds, 3 seconds? I don't know, for each of the two results, plus and minus. So you put it once into your calculator for plus, put it again into your calculator for minus, and when you do that, you find that t equals 1.6 seconds, and then t equals 2.4 seconds. So that, in a real-world sense, gives us a better idea. It is at 96 feet in the air at 1.6 seconds on the way up, and then it's at 96 feet again at 2.4 seconds on the way down. So those would be our two solutions. All right, let's move on to another example. This one, we have the length of a rectangle being 6 more than the width, and the area of the rectangle being 16 square inches. We are asked to find the length and the width. So when doing this, let's draw a picture, because this is a geometry problem, and drawing a picture of a geometry problem, not a bad idea. So we have a rectangle, and we know that the width is going to be our variable x, because the length is 6 more than that, so we're going to say x plus 6. And then we know our area is 16. So how do we find area? Length times width. So we take our length, multiply it by our width, or our width, and multiply it by our length. And that's going to equal our area, which is 16. Now we're going to just multiply out these, which gives us x squared plus 6x, and we'll go ahead and subtract 16 from each side. And now we have our quadratic equation. Now, would the quadratic formula be a smart idea for this one? Well, it would work, but I'm looking at this and I'm seeing this might be easy enough to factor. Can we find two numbers that multiply to give us negative 16 and add to give us 6? And as it turns out, we can. 8 and negative 2. So we have x plus 8 times x minus 2 equals 0. And when you split it up, you get x equals either negative 8 or 2. Now, go back and think about the problem. Does this make sense? Well, negative 8 does not make sense because we cannot have a width of negative 8. That's what our x is. You can't have negative width. You can't measure something in the negative. So we're going to discount that solution. And the solution that's left over is 2. So our width is 2 inches. Remember to put your units on it. And our length is going to be 2 plus 6 inches, which gives us 8 inches. All right, for the next example, we have Charles opening a bakery in Charlotte, North Carolina. His accountant models his profit P in dollars with the function P of T equals 560 times T minus 2 quantity squared minus 14,000, where T is the number of years of operation. Determine how long it will take for the shop to start making a profit. So let's think about this a little bit. We have a business. Are you in the positive when you start a business? And the answer to that is no, because what do you have to do when you start a business up? You have to borrow money so that you can purchase the building, purchase the equipment, get everything set up. You have to put money into the operation before you even open the operation up. So you're starting in the negative. Okay, so our profit the first couple of years at least should be expected to be negative. Eventually, you'll pay back all of those loans. And once all those loans are paid back, you'll start having positive profit. The point at which we go from negative profit to positive profit is going to be right in the middle. Between negative and positive, we have 0. So when we want to find out when we start making a profit, we're going to set P of T equal to 0. So we are going to take this equation, 560 T minus 2 quantity squared minus 14,000, and we're going to set that equal to 0. By the way, this is a very real-world type of a problem. This is what a profit equation would look like. This front part tells you how much profit you're earning or how much money your business is making each year. And this minus 14,000 part tells you how much money you borrowed in the initial cost of starting the business up. Okay? So at some point we're going to overcome that 14,000 deficit, and we're trying to find out when that is going to occur. So from here, we are going to solve it. Now, what is the best method to solve this one? Well, we have t minus 2 quantity squared. It looks very much like vertex form, right? Since we have a t and a square, and that's the only t we have, I think taking the square root would be our best option. So if that's our best option, let's go that route. We've got t minus 2 squared. We're going to add 14,000 to each side. Then we've got to divide by 560. So you've got t minus 2 squared. 14,000 divided by 560 happens to be 25. Now we're going to take the square root of each side. And when we do that, we get t minus 2 equals plus or minus 5. So t equals 2 plus or minus 5. So t is either going to be 2 plus 5, which is 7, or 2 minus 5, which is negative 3. But which of these solutions can we throw out? Well, time can't be negative. We can't go back 3 years and start making a profit. So we're going to throw out the minus 3, and so that leaves us with 7. So it will take 7 years to start making a profit. In other words, it's going to take 7 years to overcome the initial debt of starting up the business. Now, keep in mind, this is an equation that models based on current trends. If the business starts picking up and more people are coming to the business and it's becoming more successful, then that equation is going to change in a real world sense. And it won't take 7 years. It'll probably take less time to start making a profit. So remember, just because you have this one equation doesn't mean that equation is going to fit the business the entire 7 years. That equation is going to change based on how well or how badly the business is operating and how much business they are taking in. All right, let's do one more example. The total cost of renting a bulldozer and hiring an operator is described by this function, where x is the number of hours worked. Find the number of working hours if the cost is $174. So let's go ahead and set it up. We got 474 plus 31x minus 2.30x squared equals 174. This one's fairly straightforward because they tell you what c of x equals outright. All right, I want to get this into standard form, so I'm going to move my 2.30x squared to the front. I'm going to move my 474 to the back, and while I'm doing that, let's subtract the 174 from it. So that's going to give us plus 300 equals 0. Now, I know a lot of you don't like working with decimals. There's an easy fix for that. If we multiply each side by 10, or everything by 10, then we can get rid of that decimal and have negative 23x squared plus 310x plus 3,000 equals 0. Now we got to figure out how to solve it. Well, graphing may not be very practical here. Factoring, not very practical because we've got some pretty big numbers here. Same for completing the square. Big numbers, that's going to be an issue. We can't take the square root of each side because we have an x term. So what does that leave us with? The quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So we're going to put in 310 for b here and here. We've got 4. A is negative 23. C is 3,000. As usual, I didn't draw my square root nearly long enough. And then 2a. A is negative 23. So you do some of that math. You end up with negative 310 plus or minus the square root of 372,100 over negative 46. Okay? I'll let you do the math on this. The square root of 372,100 actually does come out to be even. It's a perfect square. And your solutions end up being, negative 150 over 23. And the other solution is 20. So of those two solutions, which one does not make any sense? Well, again, we're talking about time, because we're talking about the number of hours worked. So since time cannot be negative, we are going to get rid of that first answer. And so that leaves us with 20. So the answer is 20 working hours. And that is our solution. So that wraps up this section of notes. This is not all-inclusive as to every single type of real-world application that you could possibly find, but at least this gives you an idea of how to approach some of these problems, how to set them up, and hopefully that will give you enough to be able to do some fairly basic real-world problems that you would be prompted with. All right, the next section will wrap up this unit. We will be moving on to section 8, where we will be dealing with some quadratic inequalities.